Hi, welcome. So today we're going to be working on this example here. Let's go ahead and read it. A box with a square base and open top must have a volume of 32,000 centimeters cubed. We wish to find the dimensions of the box that will minimize the amount of materials being used. Okay, so every time you see a problem like this, it is important to identify what is it that we have given to us and what is it that we want to find here. Now, for this here, I'll go ahead and create a list here. Given. So what are some things here that are important that we should think about that might help me out with finding a solution here? And the first thing that I see here that can be helpful for us is going to be that we need to have a square base. So because we have a square base, we expect the length and the width of the base of the bottom part of this box to be the same. So for that reason, I'm going to go ahead and represent the base of this here as x's. They have to be the same. We have a square base. The next thing that we have to consider is open top. This is important because it's going to help us out with figuring out what we have and what we don't have for this problem here. So open top, that means that this portion here of this box is missing here. And the last thing that I see here is the volume is equal to 32,000 centimeters cubed. Now, what is it that we want? Well, as you guys can see here from the last portion, we wish to find the dimensions of the box that will minimize the amount of materials being used. So we want to figure out what materials, the amount of materials, or basically the dimensions of this, the base, the width, the height that this box must be. That will make this statement true, the volume, and that will be the minimum. So for what do we want, I'll go ahead and write it here. So we basically want to find value of dimensions, dimensions that makes the volume equal to 32,000 centimeters cubed and minimizes materials used. Now, because we are interested in finding the dimensions that will minimize the materials being used, this is going to translate to we want the lowest surface area. So in other words, minimizing this here will make this smaller, which is going to make this problem here talk about the surface area. Okay, so now that we have the given, now we have that we want, let's go ahead and figure out how to continue from or to the next step. All right, so the way that I would approach this problem here is we do have some information given to us, right? We know that the volume has to be equal to this number here. So the volume, it has to be equal to 32,000 centimeters cubed. This is a given, so we have to consider this true, and we have to make sure that this is always true here. All right, so the next thing we got to do is, well, because we don't know the dimensions of this is what we're trying to find, we're going to go ahead and just remember the formula for the volume of a figure that looks like this. Now, if you guys remember, I'll go ahead and recall volume formula. For a figure like this, it's going to be V is equal to length times width times height. Well, we know that our figure is a square base. So that means the length and the width is going to be the same. Well, what about the height? Well, it's not given to us. So for that reason, I'll go ahead and use a y here. Now, keep in mind that when you multiply this here, we have to get this number. This is a given. We have to respect it. So using these variables that I have here, we have to satisfy this condition here. And it's going to be x times y is equal to 32,000 centimeters cubed. So to simplify this here, I have x squared times y equals 32,000 centimeters cubed. And this is something that I can go ahead and work with to figure out to solve for my x and my y. Now remember, the goal for this here is going to be to find the dimensions, so find the values of x and y that is going to minimize the materials that I use. And we did conclude that we were going to look for the surface area. So the other thing that we want to maybe be interested in is finding the surface area formula for this. So surface area formula. And if you guys remember, for something like this, we like to say that the area is equal to the sum of area of all faces. So what do I mean by that? That means I am looking at the bottom portion, so that is a square. We have to find the area of that, plus the area of all the sides that we have in this figure here. Remember that this figure here does not have a top, so this is important to this part here. So for this problem here, the area is going to be, well, how about we start with the bottom part? The bottom area here, so meaning the base, remember that this is a square base. So that means that the length and the width are equal to each other. So to get the area of that rectangle is going to be length times width, which is going to be x times x, or x squared. Now let's go ahead and think about all the sides of this shape here. Well, how about we start with this one here? Well, we do know that the base has to be x. We already have that here. Well, what about the height? Well, remember that we are using y for that. So that means we're going to go ahead and add x times y, which is my base times my height for this. Now, how many sides do I have on this figure? Well, we have 4. So for that reason, I'm going to go ahead and add 3 more. So now that we have this here, x squared plus x times y plus x times y plus x times y plus x times y, I can go ahead and simplify this by combining like terms. And now I have my area is equal to x squared plus 4xy. So now I have 2 pieces of information that are going to be useful for the next step. One of the things that we see here is that both of these formulas here have the variables x and y. So what I'm going to do here is I'm going to solve for y next so that I can plug it in and create a function that I can be able to use to find the max or the min that I need for my dimensions here. All right, so now that I have this and this, I'm going to go ahead and create a new function. All right, so we were able to get these 2 equations here with the information that it was given to us. So my job now is going to be to create a new function where I combine both of these informations here, and that function is what I'm going to go ahead and use to try to find the minimum. So what I'm going to go ahead and do is solve for one of the variables, use substitution to get to use for the other one. So for this here, I'm going to go ahead and solve for y here so I can use substitution and plug into this. Why? Because remember, we want to minimize the surface area because of the surface area represents the materials that we are using. So for that reason here, I'm going to use this here to try to get a function representing the surface area using this fact here that has to be true. So what I'm going to go ahead and do is to isolate my y is I divide both sides by x squared. And now this here will cancel out with this, and I have y is equal to 32,000 centimeters cubed over x squared. Now that I did have this, we can go ahead and use substitution. So use substitution. And I'm going to go ahead and call this function here a of x to represent the surface area of this figure that we have using this information that we concluded from the information given to us. So using substitution, that's going to give me x squared plus 4x. Remember, we are substituting y. So everywhere I see a y, I'm plugging this in. So that means here I have 32,000 centimeters cubed divided by x squared. And this is surface area function. And this function here is going to satisfy the idea that the volume has to be 32,000. That is why we want to use this here. All right, so let's go ahead and simplify this here before I continue. So we have this function that we created, a of x is equal to x squared. Now notice here I have an x squared and I have an x up here. So that means this here is going to cancel out with one of these here, and I have one remaining. And the next thing I have to do is multiply 4 times 32,000 centimeters cubed, and that is going to give me plus 128,000 centimeters cubed divided by x, because I still have one x remaining there. All right, so any problem that deals with minimize, min, max, we're going to have to go ahead and use the first derivative and second derivative technique to help us out with those values. So using this formula here, what I first need to do is calculate any critical numbers. So finding the critical numbers is going to require me to find the first derivative. So because I have to find the first derivative, I'm going to rewrite this here in a way that's going to make it easy for me to take the derivative. And specifically what I mean is this x in the denominator, I'm going to go ahead and bring this to the top just to make it easy. So here we have x squared. We're not going to touch this. 128,000 x to the negative 1 cm cubed here. Now that I have it in this form here, it should be easier to calculate the first derivative. So the first derivative of this is going to be, here the derivative of this gives me 2x. Now be careful with this negative 1. When you multiply this to the front here, it's going to become negative 128,000 times x to the negative 2 cm cubed here. Now that I have this here, what is it that I want to do? Well, remember, every time I am talking about maximum and minimum, I have to make sure that I find my critical numbers. Why? Because critical numbers are essential to finding possible local max and local mins. So if you guys don't remember, let me go ahead and remind you guys. Critical numbers for our example are going to be values of x that makes the first derivative of this here equal to 0, or makes this function here undefined. All right, so let's go ahead and continue. Let me erase this here so we can go ahead and use more space to compute. Okay, so now that we have our first derivative, it's going to be a good idea to rewrite this here where your exponents are all positive. So 2 to the x is equal to 128,000 divided by x squared cm cubed. Now for the critical numbers, again, we are looking for critical numbers. For this particular problem, we're looking for when does this function here equal to 0, or when does this function here is undefined. So I want to go ahead and start with this part here. We do have a fraction portion of this function here. So what would be a value that will give us problems? So let me go ahead and copy this down again. So if you notice here, what happens when you plug in x is equal to 0? Well, if x is equal to 0, this is fine, we get 0, but here we get something that is undefined. So that means x is equal to 0 is a critical number. But is this a value that I want to use? Well, remember that we do have a requirement that we have to satisfy. And that requirement is that x squared times y must be equal to 32,000 centimeters cubed, because this is your volume. Now, what happens if you let x be 0? Well, if you let x be 0, we're saying that 0 squared times y is equal to 32,000 centimeters cubed. And will this be true? No, because 0 times anything will be equal to 0, and 0 will not be equal to this here. So for that reason here, we're going to say that this here is going to be false. it's going to fail that requirement that we have to satisfy. So for that reason, we're going to go ahead and focus on the other part and try to figure out when does this here equal to 0. And to find when this here is going to be equal to 0, what I'm going to go ahead and do is just let this here equal to 0. So that means 0 is equal to 2x minus 128,000 centimeters cubed over x squared. And what we're going to do here is we're going to solve for x to see what value is going to make this true. So what I'm going to do here is multiply both sides of this equation here by x squared. Why do I want to do that? Because when I multiply that to this part of this side of the equation, that is going to cancel out this denominator, which is what I want. I want to isolate my x here. So on this side here, we have x squared times 0. The result will be 0 equals x squared times 2x. That will give me 2x to the third power. Minus this will cancel out with my denominator here, and that will give me 128,000 centimeters cubed. Now that we have here this, we can go ahead and solve for x. So what I will do here first is add this here to both sides. So 128,000 to both sides, and we end up with 128,000. That is now positive. Cm cubed equals 2x to the third power. Divide both sides by 2 to isolate your x, and now we have 64,000 cm cubed equals x to the third power. Now, to isolate this, what we have to do now is take the cube root of both sides. Taking the cube root of both sides will cancel out this x to the third power here and just leave me with what I want, which is just an x. Now, if you plug this into your calculator, you're going to end up with the answer of x is equal to 40. And this here is what we call a critical number. Now, don't forget that here we did find two critical numbers, but one did not make sense, so we're going to go with this here. So what we want to do next is going to be to use the second derivative test to see if this here is going to be a max or a minimum. What do we want? We want it to be a minimum because we want to minimize the materials that we are using. So to verify it one more time to see if this is a minimum, we're going to use the second derivative test. All right, so let me erase this here so that we can go ahead and continue. Okay, so let's go ahead and continue, and we're going to now apply the second derivative test. Now, why do we want to apply the second derivative test? Well, simply because that is going to help me to figure out whether at the x equals to 40, if that is going to be a maximum or a minimum. So how does the second derivative test work? Well, the second derivative, remember that tells us the concavity. If it is positive at that point 40, then that means that we are concave up. And if we have concavity upward, that means that we're going to have a local minimum, which is what we want. Well, what happens if it's negative? Well, if it's negative, that gives me concave down. And if it's concave down, that gives me that at the point x equals to 40, that is what we consider a maximum. And we don't want that. We want the minimum for this. So let's go ahead and compute the second derivative of this. So taking the second derivative here, what happens to this part here? Well, we end up with just 2. How about here? We multiply this times this. So notice negative times negative, that will become positive, and that will give me plus 256,000 x to the negative 3 cm cubed. And let me go ahead and just make the power positive now. So just these two are equivalent here. Divided by x to the third power cm cubed. All right, so now that we have this here, again, we're going to go ahead and plug in our value 40. Let's recall that x equals to 40 is a critical number. So what we're going to do now is we're going to plug it into the second derivative to check if we have concave up or concave down. So if I plug this in, I'm going to plug in x everywhere. I'm going to plug in 40 everywhere I see an x here. So I have 2 plus 256,000 divided by 40 raised to the third power, and this will be cm cubed. Now here we have to use a calculator for this, and when you plug in this in your calculator, you are going to get that the second derivative when you plug in 40 is going to be equal to 2 plus 4, which is equal to 6. Now notice here this is positive, right? So because this is positive, 6 is greater than 0. So that means we have concave up. And if we have concave up, this implies that when x equals to 40, we have a minimum, which is what we were interested in. We wanted this to happen. So now we have the value of x that is going to give me a minimum. But remember, we have x's and y's. So now we're going to have to try to solve for y, knowing that we already found what we needed for x, which is this here. All right. All right, so let's go ahead and continue here. So we already verified that when x is equal to 40, we have a minimum. Now we want to solve for y. So we want to find y. So how do we do that? Well, we'll go back to the original equation that we were using, and that is the volume formula. Remember that the volume was given to us. So all we got to do now is use it by plugging in this value and solving for y. So if you guys don't remember, we had x squared times y equals to 32,000. This has to be true. This is one of the requirements that we have to satisfy. Well, we now have the value of x squared, and that's going to be 40 squared times y. We don't know what this is equal to 32,000 centimeters cubed. We want to isolate y. So here we're going to go ahead and divide both sides by 40 squared. 40 squared. That cancels out here on this side. And now on the other side here, we have y is equal to 32,000 cm cubed. Now if you plug in 40 squared to your calculator, you should get 1,600. Now I can go ahead and solve for y. And by dividing this here, we get that y has to be equal to 20. And this is going to be the dimensions that I want that are going to minimize the materials that I use for the figure. So that means going back, putting everything together, x is equal to 20, y is equal to, oops, I'm sorry, I mixed this up. That's okay. X is equal to 40. We verify that this is a minimum. We use this information to solve for y. So that means that the height has to be equal to 20. So base has to be 40. Remember the figure that we have. And this has to be my height. And these are going to be the dimensions. That minimizes the supplies or materials used. All right, so I hope this helped. Thank you.